Quantum chromodynamics is the branch of theoretical physics that describes how the strong nuclear force operates at the subatomic level. It is a part of the Standard Model of particle physics and provides the framework for understanding how quarks and gluons, the building blocks of protons, neutrons, and other hadrons, interact and bind together. The strong force is one of the four fundamental forces in nature, alongside gravity, electromagnetism, and the weak nuclear force, but it is by far the strongest of them, responsible for holding the atomic nucleus together despite the repulsion between positively charged protons. QCD was developed in the 1970s as physicists sought to better understand the behavior of hadrons and the internal structure of nucleons. It is a quantum field theory based on the gauge group SU-3, which governs the interactions between quarks through the exchange of particles called gluons. Just as photons are the force carriers of electromagnetism, gluons are the force carriers of the strong interaction. However, unlike photons, which do not interact with each other, gluons do carry color charge and interact with one another, making QCD highly nonlinear and complex. The central idea of QCD is the concept of color charge. Quarks come in three colors: red, green, and blue, and gluons act to constantly exchange these colors between quarks, maintaining what's known as color confinement. This means that quarks are never observed in isolation, they are always confined within larger particles like protons and neutrons. If one tries to separate two quarks, the energy used pulls them apart to such an extent that new quark-antiquark pairs are spontaneously created, forming new hadrons instead of isolated quarks. One of the most fascinating features of QCD is asymptotic freedom, the phenomenon where the strength of the strong force becomes weaker as quarks come closer together at high energies or short distances. Conversely, at larger distances, the force becomes stronger, which is why quarks are tightly bound within nucleons and cannot be pulled apart. This property was confirmed in deep inelastic scattering experiments and led to the Nobel Prize in Physics in 2004 for David Gross, Frank Wilczek, and David Politzer. QCD has been tested through high-energy particle collisions in accelerators like CERN's Large Hadron Collider, where jets of particles provide indirect evidence of quark and gluon dynamics. However, many challenges remain in solving the equations of QCD exactly due to their mathematical complexity. Researchers use computational methods such as lattice QCD, which discretizes spacetime into a grid to simulate quark-gluon interactions numerically. Quantum chromodynamics remains one of the most successful yet challenging theories in modern physics. It not only explains how visible matter is structured at the deepest level but also plays a critical role in cosmology, nuclear physics, and the quest for a unified theory. As we continue to probe the quantum fabric of the universe, QCD stands as a pillar of our understanding of the atomic nucleus and the fundamental particles that make up everything we see.